Some, perhaps all of you, have noticed by now that the scores for exam 2 for a number of you have changed. And for those who experienced score changes, most went up, because I had 2 questions miskeyed on exam 2. The key has been repaired, the correct key is now posted, and the correct scores for exam 2 are now shown. On with electrochemistry. Language, some of which we talked about last time, but it's important, so we'll repeat. Oxidation, abbreviated as such. A half reaction, which we'll talk about in greater detail in a moment, showing an increase in oxidation number as a reactant converts to product. Example, sodium per atom loses 1 electron, becomes sodium ion. Expected chemistry, because as you know, the 1A metals show only this kind of behavior in their chemistry. Couple of minor exceptions, we'll not concern ourselves with such at this time. Reduction, chemical process in which oxidation number decreases as reactant converts to product. Like elemental halogen, a potent oxidizer. Per atom, chlorine collects an electron, becomes the chloride ion. And by now you should have recognized that the only negative oxidation state shown by the atoms of family 7A, the halogens, -1. Because when a halogen atom collects an electron and becomes an anion with a charge of -1, it now has an electron configuration, a valence electron configuration, which is isoelectronic with that of its nearest neighbor. You remember the word isoelectronic from 2045? Means same electron configuration as. Now, half reactions. The way by which we can analyze redox reactions and their progress systematically and understand the chemistry which takes place in a redox reaction is by what we call the half reaction method. Because every redox reaction involves 2 parts. The part corresponding to oxidation, the part corresponding to reduction. The half reactions show a separation of these 2 parts. Half reaction for oxidation, half reaction for reduction. And we'll also see this is an important consideration based on the fact that when an electrochemical cell is manufactured and operates, are you familiar with any operating electrochemical cells which deliver usable electrical energy? Are you familiar with batteries and flashlights and car batteries, stuff like that? In order to prevent what the electrical folks call a short circuit, you have to physically separate the hot oxidation process from the reduction process. We'll show you why and how in a moment. Now, what do we do with the half reactions? We recognize that a redox reaction, like any chemical reaction system, must react in accord with the principles of conservation of mass and energy. That means there cannot be any net liberation of electrons nor net consumption of electrons. The redox reaction must, like all reactions, balance with respect to mass and charge. So what do we do with the half reactions to get the net redox reaction? We apply to them a process known as coupling. More on that in just a moment. Which means you take the half reaction, which shows oxidation, the half reaction, which shows reduction, and as necessary, adjust coefficients for each reaction so that when you add the half reactions together, total electrons produced by the half reaction showing oxidation equals total electrons consumed by the half reaction showing reduction. That way, when you add up the halves, you get a redox reaction in which there is no net consumption or liberation of electrons, because that's impossible. Now, to eliminate fractional coefficients, what I did here was to multiply this by 2 as well as this by 2. And rewrote those half reactions like this, and now I coupled them. I added them together because as these half reactions are now written, total moles of electrons liberated counterbalances total moles of electrons required or consumed. So here's the net redox reaction for what takes place if you put sodium in the presence of chlorine. If you want to run this reaction, let me know. Especially if you wish to use large quantities of sodium and chlorine, because I want to get the hell out of the way. This is an exceptionally violent, strongly exothermic process. Boom! Now here's an exothermic spontaneous transformation which takes place with an unfavorable change in entropy. Shouldn't be too surprising to you. But an ionic lattice is a rigid, strong, stable lattice, whereas this is a gas. And sodium metal is a metal which has not a strong lattice at all. You can take sodium metal and cut it easily with a butter knife. But sodium chloride, big crystal, strong crystal lattice, high lattice energy. So in this net redox reaction, sodium has experienced oxidation while causing reduction. That's why sodium is the reducer. Chlorine has experienced reduction while causing oxidation. So chlorine is the oxidizer. And as we looked at the reaction last time, with hydrogen combining with oxygen to make water, where water, since it was the only product, had to be simultaneously the oxidation product as well as the reduction product. Same thing here. Now, if you said that sodium chloride is the oxidation product because it contains sodium ion, the stuff produced by oxidation, and this is the reduction product because it contains chloride ion, the stuff produced by reduction, that's fine. Now, more on coupling. Look at the table in chapter 22, the table of half reactions. Number 1, realize that this table of information is read, practically speaking, just like you read the acid-base table. As I have written this table, the reducers are on the left, and the oxidation product, or products, are on the right. Because as the reducer does its thing, it gets converted to the oxidation product or products. Also notice, as with our acid-base table, the acids are listed in order of going stronger to weaker from top to bottom. That's the way this table is. The strongest reducer in our table is at the top of the table, lithium. Shown in the half reaction where lithium in the presence of water converts to Li plus AQ. What is the weakest reducer in our table? What is it? Fluoride ion. Tell me, based on the information in the table, do you expect it to be possible to produce elemental fluorine by redox?
An electrode.
Well, never mind the electrode. I'm asking chemically, using the half reactions which are listed in our table. You think it's possible to produce elemental fluorine chemically? Because in order to produce elemental fluorine chemically, you've got to have something which can oxidize fluoride ion. And in our table, fluoride ion is the weakest reducer. So what the heck's going to oxidize fluoride ion? If fluoride ion is the weakest reducer, anything which it reduces will become a stronger reducer. And you'll be looking at a reaction which is not going to go anyplace practically from a thermodynamic standpoint. Does that make sense? Just like the acid-base table. Strongest acid at the top, in the acid column, weakest acid at the bottom. Weakest base at the top. So in our table, what's the weakest oxidizer which you see? What is it? What's the weakest oxidizer in our table? Li plus Aq. Is Li plus Aq the weakest oxidizer in our table? Capable of being reduced by any reducer in our table? Name the reducer in the table which can reduce Li plus Aq. Is there any? I'm asking you to learn how to read the table, not to scan the table feverishly looking for some stuff which by magic you can now decide is capable of reducing Li plus. There's only one stuff in this table which can reduce Li plus. We'll talk about this later. What is it? I heard it. Lithium. Lithium can reduce Li plus. Just like Li plus can oxidize lithium. You remember in an ammonium ion ammonia system, the main acid-base reaction is between ammonium ion and ammonia? But that doesn't get you any place from an H plus exchange standpoint. But we will realize that by Li reducing Li plus while simultaneously Li plus oxidizes Li, that we can build an electrochemical cell which gives us usable electrical energy known as a concentration cell. More on that later, not now. For now, I ask that you accept the statement that practically there's nothing in the table which can reduce Li plus, just like there's nothing in the table which can oxidize Li, which can oxidize fluoride ion, pardon me. Now then, based on the table, which oxidizer-reducer combo would you expect to give you the most vigorous redox reaction? Lithium metal and elemental fluorine. If you make that mix, get the hell out of the way. Very far out of the way. All right? Now then, keep looking at the table. Coupling, which we'll illustrate with a demonstration in a moment. Pick any two half reactions. It doesn't matter. Pick any two half reactions. That's directive number one. Directive number two. Take the half reaction, which involves the weaker reducer, Or from a number standpoint, take the half reaction, which as I've constructed this table has the smaller E0 value. Because E0 measures the tendency for the reducer in each half reaction to convert to its conjugate oxidizer. Acid converts to conjugate base, base converts to conjugate acid, reducer converts to conjugate oxidizer, oxidizer converts to conjugate reducer. Just like acid-base stuff. Different types of materials from a reaction nature standpoint, the language applies. Take the half reaction of lower E0 because it contains the weaker reducer and write that in the opposite direction. Then make coefficient adjustments like I did here so that when you add these halves together, electrons cancel. Moles of electrons produced equals moles of electrons consumed. But when you make these coefficient adjustments, do not multiply the E0 value. The only thing you do to E0 is in reversing the half reaction of lower E0. In reversing the half reaction which contains the weaker reducer, what do you do to E0? Change the sign, that's it. And now add them up, and what you get is E0 for the net cell reaction. And if you couple half reactions as we have just directed you, you will always get an E0 which is positive, which means you are looking at a redox reaction which is spontaneous or not spontaneous. Spontaneous, because positive E0. E0 means tendency to happen. Electrochemical potential. What's the potential for this to take place? If it's positive, it's thermodynamically spontaneous. All right? Now please, take a look at the cell diagram you see on page 22A. And at the same time, look at the table to find the half reactions which I'm now going to write on the board. Notice that I've written the second half reaction so that we can couple it with the first half reaction. Notice in the table that the half reaction which shows zinc, metal, in the presence of water, converting to hydrated zinc ion with the loss of 2 electrons because the only positive oxidation state that zinc ever shows in its chemistry is +2. And the half reaction which involves copper metal in the presence of water, converting to hydrated copper ion with the loss of 2 electrons because the most common oxidation state shown by copper in its chemistry, positive oxidation state, is +2. The copper-copper ion half reaction has the smaller E0 value because copper is not nearly as strong a reducer as is zinc. What's that mean? That means that zinc can spontaneously reduce the conjugate oxidizer of copper, which is hydrated copper ion. And it also means that copper, which is the conjugate reducer of hydrated copper ion, cannot reduce hydrated zinc ion. because hydrated zinc ion is a weaker oxidizer than hydrated copper ion, and zinc is a stronger reducer than copper. So here's these two half reactions coupled. Since 2 moles of electrons liberated, 2 moles of electrons required, I can add them up straight away and write the reaction equation, net redox reaction equation. For this electrolytic system, for this redox reaction system. Now perhaps you recall in 2045L, we had to do this kind of stuff. If I have a sample of zinc metal and a sample of copper metal, and a solution containing hydrated copper ion, I ran out of 1 molar, so here's half molar copper sulfate solution. And a solution containing hydrated zinc ion, 1 molar zinc sulfate solution. I have all that's necessary to develop the half reaction equations which you see here on the board. I have all that's necessary to find out which is the stronger reducer, zinc or copper, which is the stronger oxidizer, hydrated copper ion or hydrated zinc ion. You did this in 45L. Remember what you did? At this point, we're imagining. We have copper, zinc sulfate solution, copper sulfate solution. We don't know which is the stronger reducer, copper or zinc. We don't know which is the stronger oxidizer, hydrated copper ion or hydrated zinc ion. We don't know. How do we find out? Simple. We take the copper strip and put it in contact with hydrated zinc ion. Recognizing that if copper can reduce hydrated zinc ion spontaneously as the copper strip stays in contact with hydrated zinc ion, we're going to get a deposit of zinc on the copper surface. And as copper goes into solution as hydrated copper ion, as time passes, do you think this solution will develop a color? Yeah. It'll get blue, because hydrated copper ion is a bluish colored ion. How many of you in 46L in assignment 6 by now? Well, then you've done some work with this. Now then, here with the copper in contact with hydrated zinc ion, nothing's happening. Of course, we already know that. Now here with the zinc strip in the second beaker, let's put in a source of copper ion, hydrated copper ion. Notice that. As soon as the hydrated copper ions touch the zinc strip, we got a deposit on the zinc strip. Now this deposit hardly looks like copper. But if I allow this to stand in the presence of copper ion for a while, you'll see the development of the bronzish color that we are familiar with regarding copper. The point is, we don't see the bronzish color form immediately because the deposit of copper, which we obtained, known as copper black, is formed so rapidly that we are not yet developing any copper lattice of consequence, which is necessary to do in order to see the bronzish copper. If I allow this to stand in here for a good while, you'll see the bronzish copper color develop. Now, unfortunately, we won't be able to see this with the camera, but if I take this where you can see it really closely, You see at the tip of this, see the bronzish color?
Yeah.
If we leave it standing there, you'll see it. I mean, it's hard to see, I admit, but the more copper I deposit on the zinc strip, the more difficulty I have in cleaning the zinc strip for the next time I want to do this. So I'll stop the reaction. In any case, secondly, take note that with the transformation, I'll put it back in there, that we are now observing, we have what is known as a short circuit. Electrons are flowing. An electrical current is traveling. It's traveling from the zinc strip to the copper ions. Unfortunately, we are not able to harness the energy associated with this current because for the system as we have constructed it, the zinc atoms are losing electrons directly to the copper ions. And if we want to use these electrons to do usable electrical work, we've got to make the electrons flow through an external circuit. How can we do that? Now we got a lot more bronzish on there. And if you're interested, you can come and take a look after our chat. Here's how we do it, or a way to do it. In a beaker, we're going to put some zinc sulfate solution and a strip of zinc. Now we have that here. In a second beaker, we're going to put copper strip in copper sulfate solution. We have that here. When you sketch these things, it's standard practice to sketch the half cell, because in a half cell, a half reaction occurs. It's standard practice to sketch the half cell on the left in which oxidation takes place. And the half cell sketched on the right will be the half cell in which reduction takes place. So in this half cell, after we assemble it, zinc, the anode material, where the anode is the electrode at which oxidation occurs. The anode material, zinc, will convert to hydrated zinc ion in this half cell. This half reaction will occur. And as that takes place, electrons will travel through our external circuit. And in our external circuit, I've connected an imaginary meter so we can monitor electron flow. But now we're being able to use the electrons because we forced them to travel through this external circuit. Just like you force electrons to travel through, well, you don't do it, but GRU does it for you. Forces the electrons to flow through external circuitry in your home. And then you can use this electrical energy as necessary. The electrons travel through the device which we wish to power and travel into the cathode material, which in this case is our copper strip. Well then, as electrons travel into the copper strip, this plate keeps on being made negative from a charge standpoint, because electrons are negative. So the positive things in this solution, what are the positive things in this solution? Hydrated copper ions. They travel over to this strip and on its surface collect these electrons and become copper atoms, depositing on the surface of this strip. Now, so far we've shown the electrons traveling in only one direction. From the zinc to the copper strip, the surface on which copper ions collect electrons and become copper metal. But if we're going to have a complete circuit, we've got to provide a pathway by which current can flow this way, back into this cell. This current that flows from this half cell to this half cell will go through this gadget called a salt bridge. Is the current which flows through here a collection of electrons, a stream of electrons? What is it? What is the current that flows through the salt bridge? A stream of ions. Negative ions going this way. Why would negative ions go this way in this system? Why would negative ions tend to go this way? Aren't zinc atoms becoming positive ions over here as they lose electrons? Well then, as this process takes place, this strip continues to be made positive, and negative things travel toward the positive. Coulomb's law. So let's take a look at this system in operation. Here we have the copper in the copper ion solution, the zinc in the zinc ion solution. They're in separate beakers, so we're separating reduction from oxidation. As things stand, however, we cannot have reduction and oxidation because we have not got these systems connected. Well, let's connect these systems. I've got here a gizmo which will read voltage. Of course, we're not going to read current because the current we get from this is so very, very small. The resistance of a salt bridge is extreme. So all we can really measure successfully with this kind of demonstration is potential. Now, while I make the connection, take a look at E0 for this half reaction and E0 for this half reaction. Keeping in mind that for this copper-copper ion half reaction, we wrote it in the opposite direction. So that involves changing sign on that E0 value. What should we get when we add these E0 values together? What should we get for the E0 for the net reaction, which is this? What should we get?
The number is 1.10.
1.10 volt, look right? I need an observer. Who wants to be an observer? You did it last time. You can be the observer. Yes, you. I'm going to switch this. Don't stand in the way. You're the observer, not the blocker. I'm going to turn this to read voltage. Uh-oh! We're jumping all over the place. We're not getting anything yet. Why not? Where's the salt bridge? We didn't connect the systems yet. Come on over here, observer. Hold this. Don't move it. Don't move it at all. Freeze. Salt bridge. The salt bridge I have here is an agar paste saturated with potassium chloride. Potassium ions, chloride ions, neither of these react with the components of this system. Otherwise, we'd foul up the system electrochemically speaking. Now, I may have to lift this because the salt bridge arms are not the same length. What do we got now?
1.083.
1.083. Staying there?
Yes, sir.
Okay, I'm not surprised because, remember, these half cells are, for standard conditions, I mean the E0 values given for these half cells are standard state conditions, and I don't have standard state copper ion. I got half molar copper ion because I ran out of the 1 molar copper ion, and I didn't have time to make any new stuff. Terrible, but now at least we see how it works. Thank you.
Okay.
I'll put that together later. Now, please make the fixes regarding the cell diagram that you see on page 22.8 in the notes. The cell diagram in the notes has the anode half cell mislabeled. It says cathode. Notice that each half cell is labeled cathode. Not right. Strike cathode for the zinc ion half cell and write in anode. Secondly, the half cell on the right contains copper ion, not calcium ion. Fix that. I didn't notice these things when the daggone notes were typed. Also, the zinc ion is really hydrated zinc ion. The copper ion is really hydrated copper ion. So you can write these formulas correctly. Keep in mind, and as you become more familiar with usage of the information in the half reaction table, electrochemical processes very often involve complex ions. So we're now going to more heavily use the information which we talked about in brief at the end of chapter 19 on complex ions and their stabilities. Because what this half reaction table really is, just like the acid-base table, is a compilation of thermodynamic stabilities. What have we now realized? Which material is more thermodynamically stable from a redox standpoint? Copper or zinc? Which one is more stable, copper or zinc? Copper. Because it's the weaker reducer. It has the lower tendency to change and become something else. Which material is more thermodynamically stable? Hydrated zinc ion or hydrated copper ion? Which one? Hydrated zinc ion. Because it's the weaker oxidizer. It has the smaller tendency to change and become something else. Let's take a look at these questions. How do the ions flow direction-wise? We talked about that. The positive ions go toward the cathode because the cathode, as the system is in operation, continues to become enriched in negative charge. Negative ions flow toward the anode because as this system reacts, as the system changes, the anode continues to become enriched in positive charge. Write the equations and half reactions. We've done that. Calculate E0 cell. You've seen that E0 cell equals plus 0.76 volts plus 0.34 volts, because minus 0.34 volts becomes plus 0.34 volts when we take this half reaction and reverse it. How long will the cell operate?
It's until zinc or copper, hydrated copper runs out, whichever is less.
Are you sure?
Well, I suppose it depends on which one you have more of, but it could also be when the salt bridge runs out of ions to contribute.
How long will this cell function so as to give us usable electrical energy? Until what is achieved? Equilibrium! Now, take note that for just about every redox reaction, at least every one with which I am familiar, K values are usually very large. What does that mean? That means redox reactions are essentially one-way streets. Very large K values. Not like a number of acid-base reactions. Now then, last question, 2210. Here's our system. I'm going to supply you with 6 molar ammonia. Clue, hint. This question is about getting you familiar with using the information in this half reaction table. 6 molar ammonia. I am saying, by use of 6 molar ammonia, is it possible to operate on this electrochemical system so as to create a system which will give us a larger E0 value? Now let's look at what we could do. We could add the ammonia to the zinc ion half cell only. We could add the ammonia to the copper ion half cell only. We could add the ammonia to both half cells, or it might be true that the system as it presently operates is giving us an operating potential which is larger than any potential we could achieve by treating either or both half cells with ammonia. So you got 4 choices. Ammonia, this half cell only. Ammonia, this half cell only. Ammonia, both half cells. Ammonia, neither half cell. One of these 4 is correct. Which is it? Well, let's finish with a vote. Are you looking at the table of half reactions? The answer is A, add ammonia to the anode half cell only, the zinc ion half cell. That's correct. I don't feel like fishing for any other answers. Because if you look at the table, it tells you, if you put ammonia in the zinc ion half cell, zinc will now be oxidized, but no longer to this. Now zinc will be oxidized to this. How does the stability of this, the thermodynamic stability of this, compare to the thermodynamic stability of this? Which one is more stable? This stuff. And what happens to the E0 value? 0.76 when I'm oxidizing zinc to hydrated zinc ion. When I oxidize zinc to the ammonia complex, what's the value? 1.04. I gave it a pretty good boost in E0. But also note, if I choose to put ammonia in this half cell, now I'm going to convert my oxidizer, which is hydrated copper ion, to this stuff. Is this the copper ammonia complex ion? Is this a stronger oxidizer or a weaker oxidizer than hydrated copper ion? It's a weaker oxidizer. Why is that? Because that stuff is more stable. Bingo. We'll pick it up from this point next time.